In this lab, we will be observing a magnet as it falls through a conductive tube. We will then model the forces on the magnet in a computer program using Faraday's law, the Biot-Savart law, and Newton's second and third laws. I will detail my expectations, observations, measurements, and results. Based on the lecture for Faraday's law, I expected the magnet to be affected by the upward magnetic field generated by the roll of aluminum foil, but only slightly, given the mass of the magnet. I was pleasantly surprised to observe that the magnet noticeably slowed down as it was dropped through the aluminum roll. The average time came out to 1.63 seconds. We were then tasked with completing a computer model to simulate this same experiment using the concepts gone over in the previous lecture. I first entered in the dimensions of the aluminum roll and the measured dipole moment. However, I do not believe the app I used for measuring the magnetic field of the magnet was very accurate given the results I saw when running the simulation. I then adapted the function from Lab 3 for calculating the magnetic field. Next, I completed the function to calculate the magnetic field as it changed over time. Using Faraday's law, I derived the induced current from the magnetic flux. From the magnetic field, I used the Biot-Savart law to calculate the magnetic force being applied on a ringed section of the conductive tube, and therefore, from Newton's third law, the force the ring was applying to the falling magnet. I then filled in the net force being applied to the magnet by gravity and the magnetic field from the tube. Lastly, using Newton's second law, the velocity and the position vectors of the magnet were properly updated. Towards the end of the lab, a series of questions were posed to interpret the simulation. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current, as viewed from above, and which counterclockwise? How can you know? Blue is clockwise, red is counterclockwise. We know this because of Lenz's law, that the induced current generates a magnetic field to oppose the magnet. That only happens when it is going counterclockwise. What happens to the dynamics of the system when you flip the magnet around? When I attempted to change the code to flip the magnet, the colors changed, but it took the exact same amount of time for the simulation to run. Since Lenz's law would imply that there would still be an opposing magnetic field, this seemed to make sense. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? In reality, it took less time for the magnet to fall through than in the simulation. I attribute that to a not quite accurate value for the magnetic dipole moment. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The shape of the plot shows that the magnetic field generated by the tube is strong enough to stop the magnet from accelerating as it falls, right up until it gets to the end of the tube. There were also some what-if questions we were asked to answer. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Since the resistance is proportional to the resistivity of the conductor, it would also be close to zero. And, as current is inversely proportional to resistance, the current would increase dramatically, as would the magnetic fields between the conductive tube and the magnet, slowing the magnet down even further. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnitude of the ring currents would drop as there would be less conductive material to generate an opposing magnetic field, allowing the magnet to fall faster. Thank you very much for your time.